Good evening. Can you hear me? Can you hear me? Hello. Hello. Can you hear me?
Hello. Yes, I can hear you.
Okay. So let's go start our today's session. So basically, today discuss about that. Today is our last class for aqua crop. Okay. After that, we discuss about the machine learning. Okay. Further class, we discuss about the machine learning, how to work. Yep. So today is our last class for the aqua crop. For breathing research and practice in crop water modeling. So it is try to discuss about this topic, and I'll show you some practical things. Yeah.
Okay.
So this is the one kind of simulating climate change impact. Okay, on our crop yield prediction. Okay, climate change impact on our crop yield prediction. We try to discuss about that using aqua crop os.py. This Python library we try to use, and we bridging research and practice in crop water modeling and simulating climate change impact with aqua crop. So in this case, basically, we simply translating rigorous FAO methodological into an accessible, scalable, and Python environment for analysts and agronomists. So this is our open source library, okay, aquacropos.py. So Python engine for its provide FAO aquacrop, okay, provided this aquacrop os.py, and we simply running this model and also estimate the water demand and also optimizing the management and also projecting the climate impact. Okay, in this time we just focus this part, projecting climate impact of crop yield, okay, based on the climate, based on the climate. So in this case, we simply apply this location. Okay, we have this type of data, location baseline, Campion in Nebraska, and it's available from the data 1982 to 2018. And we also apply the climate projection, basically driven by LAR's weather generate based on the ECR climate model output, and analyzing three distinct periods, basically 2021 to 2040, then 2041 to 2060, and 2061 to 2080 across the two emission pathway. One is the RCP 4.5, another is the RCP 8.5. Okay. Project using Sway. So first of all, the computational pipeline, weather data and simulation. So ingest LWRS or WG output, basically extract 100 years of daily generated climate projection. So it extract basically precipitation, then mean max temperature, then solar radiation. After that, we simply calculate the evapotranspiration, ET, evapotranspiration, process the raw input using the Hargreaves and ETU method to estimate the reference evapotranspiration, and finally structure the data frame, package the 100 years of daily data into a standardized weather data frame, directly consumable by the aqua crop OS by model or function. Okay, we also apply this type of things. So in this case, we simply choose our crop, suppose maize, okay, maize, and then we simply set the time mode. Time mode basically ensure the growing season Length remains identical across all future scenarios for accurate baseline comparison. And also soil profile, suppose clay loam, okay, starting the state initialized at the field capacity. And finally, management policy, threshold irrigation. Suppose 70% of total available water, TAW. Policy triggers irrigation only when soil drops below 70% total available water. Ensure full crop water requirement are met. Okay? So this is the agronomic environment. We simply set up this way. Our agronomic environment. First of all, crop, then time mode, then soil profile, and finally management policy threshold. TAW. Okay, total available water. Suppose 70% of total available water. Ensure for full crop water requirement are met. After that, yield trajectories a steady upward shift again. So under the both RCP 4.5 and RCP 8.5 emission scenarios, median yield project a steady progressive increase across all future time horizon. Okay, so increase and baseline yields incur at approximately 3.5 to 13.5 to 14 ton per hectare. Okay, so the highest yield cluster in the most severe mission scenario. So we also apply this type of things and then check the future scenario also. Okay, for 2021 to 2040, then 2001 to 2040, 2041 to 2060, 2041 to the 2061 to 2080. Okay, so different types of scenario we try to check. Help of RCP 4.5 and also RCP 8.5. So now irrigation demand, we also try to check it, decrease the median persistent violet. We also try to check the irrigation demand, okay, hectare per millimeter, okay, try to check it, different on the different types of model, RCP and also RCP 8.5 and also RCP 4.5, okay. And then also increasing the precipitation observation, okay, we try to check this type of things. And finally, understanding the driver escalating evapotranspiration. So this is a climate data into adaptation strategies. So powerful ingression, dynamic simulation, and also actionable insight. So let's go try to check one by one example. It will be better. Okay, let me open. Let me open a code editor. App. A new notebook. So first of all, simply install some packages, which package we need for our analysis. So simply install first time. Suppose I simply apply if install some package. First of all, aqua crop. Then also we need to also PQDM This is the one kind of Python package. Then matplotlib, and seaborn. So this type of package is simple installed in our system. So now it's successfully done. So now we simply import some more library. I need suppose from Aqua crop. I need to import on library. It's called the Aqua crop model. So Aqua crop model. Aqua crop model. So this library. As also I need the soil. So just put the soil. Then put crop. And also need other, suppose I need the initial water content. So initial water content, and also need carbon dioxide, CO, carbon dioxide, and also need irrigation management. So irrigation management. So just I simply import all of those. So this type of library I need. It's come from Aquacrop. Aquacrop is the module, okay, and this type of library. So this type of library, Aquacrop model, soil crop, initial water content, carbon dioxide, irrigation management. It's come from Aquacrop module. Okay, this type of library come from Aquacrop module. Okay, so this is the module and this is the library. So this type of library is stored in this module. So now we also need also other suppose also need we need the, okay, for the data. So we simply from Aquacrop utils and import two library. One is that get file path. It's mainly give you the file data, as well also another, it's called that per weather data, or it will call the prepare large weather. Okay, so now it talk about this large LARS. Okay, large weather. So I simply call this large weather, and also select large WFT. These things. Okay, we need simply import all of those. As well as also import another pandas library. So import pandas as PD. Just so this type of library we need. We simply imported Aquacrop, and from the Aquacrop we simply find out this type of library, Aquacrop model, soil. Okay, so this is the Aquacrop os.py. Mean it's basically this model crop growth and water use simulation we also apply. And WRS, this one WRS weather. So basically weather generate. So this it help you to create the weather generate data, and also climate scenario. Okay, so in this time we simply use the two climate scenario, RCP4.5 and also and RCP8.5. Okay, so I also note down this type of thing also help you when you revision. Suppose we try to apply. In this time we simply apply our workflow. So we simply import historical weather data. We have historical weather data, and we are use it, and then we simply create future. We will say apply future climate scenario, future climate scenarios, and then we simply apply aqua crop model, model, then identify crop growth, so crop growth, or yield. Okay, crop growth or yield, same. Okay. Crop growth or yield, and finally we also identify irrigation and water demand. Okay, so this is our workflow final. So we simply identify historical weather data we have, then future climate scenario we try to identify, then aqua crop model, crop growth and yield, and also identify irrigation, water, and demand. So this one. So in this case, we already know this type of thing. Suppose this aqua crop OSPY. So basically this one indicating about that crop growth and water use. Okay? Crop growth and water use simulation we can identify using this. It's one kind of Python library. So after that, another one we also know WRS, WG. So it's one kind of weather generator. Okay, weather data generator. So weather generator. Then also RCP, it's 4.5 and RCP 8.5. So this is the climate scenario. Okay, it's called the climate scenario. Climate scenarios. Okay. So for this, we simply import this type of library. So we simply import all of library we say need. And also import the pandas library. Okay. Weather data, soil data, crop, water, and growth. So simply identify all of those. And this is the, you can see carbon dioxide. So it's mainly indicating about that it's defined atmospheric carbon dioxide concentration. Okay. So it defines atmospheric carbon dioxide concentration. This is particularly relevant for climate change simulation because atmospheric carbon dioxide changes under the different scenario. Okay. Then irrigation management, we already know about that. Irrigation management defines how irrigation is applied. Okay. So for example, you can specify irrigation based on fixed irrigation schedule, soil water depletion, irrigation threshold, okay, or irrigation amount. We already know these type of things for irrigation management. So this one basically indicating about that atmospheric carbon dioxide concentration here. And we also agency also applied the get file. So get file, it's used to obtain the location or path of required data. Okay. And we also use suppose we also use prepare LRS weather. So this one, so this is very important. It prepare LARS WG weather data into a format that Aquacrop can understand. Okay, so it generate the WRS weather data format. Okay, because this WRS WG, this is another data format. So Aquacrop easily understand this data format. This library help you to the prepare the WLARS weather data format. and then select LRS WDP. This is the function used to select or process LRS weather data. Okay, so this one, select LRS WDP. So now we simply apply our data. So now we simply load our data. Suppose just I take a variable LARS FP equal. I simply call the file path. I call the CP. This name is a CP dot DAT. So let me import. There's a get file. Sorry. Get file function. Just take copy and run it. Okay, done. So now we try to check the data. So you can see it loaded this type of data. So now we try to read this data. So take a variable LARS phase and call the prepare LARS weather. This one, this library simply call, and then we prepare our data. And then call this LRS. Okay, and if I run the code, okay, one requirement is missing year. So which year you need? You also need to mention. Or suppose okay, so I need all of data. Okay, so for that is simply start from suppose first data. So for that I just put the inverse one. So it start from the last, then put the false. So now let's see what happened. Okay, it's working. And now I want to check the data. Run the code. So now it give me the, you can see this type of information. It's from the 1981. Okay. So it's available from the 1981. Okay. So it's available from 1981. And we find out that this type of column if you check. So there are the total 5 columns in this data. So we find out that all of information about the minimum temperature, maximum temperature, precipitation, okay, and also get the radiation. Or if you want, you can also apply suppose dot head function. Get only for the first item. Eyebrow, we find out that. So minimum, maximum, precipitation, reference, ET, and date. We find out this type of data. If you want, you can also make the list all of column. Okay. Suppose I simply create order and make the list all of column. Suppose I need the one column for suppose year. So you can see it show the some reference year, then ZA, minimum temperature, maximum temperature, precip, and rate. So wind is sped for 3.4. Okay. So just I use it all of those. Okay. So just I copy and then paste here and make the list, make the order. Okay. So now run the code again. And also run the code this one. So we find out this type of value. Okay. So for each combination of climate scenario and projection period, read in climate data and save the weather data frame. So for that, we simply choose our prediction year. Okay. And also RCP 4.5 and 8.5. So two model basically we simply apply RCP. This if you check right, RCP 4.5 and RCP 8.5 climate scenario. So we simply choose the two climate scenario. Okay. So for that we simply take a new cell and take the variable suppose RCP list and make the list suppose 445 and also 85. Okay. 4.5 and 8.5. We just consider 45 and 85. Okay. RCP list. And also make the year list. Suppose year list. We make the projection suppose 2030, then 2050, then 2070. And also range, we also set the range year range list. Suppose year range list. So for that, we simply put our range. Okay, put the range. Suppose 2021 to 2040, and 2041 to 2060, then 2061 to 2080. Okay, make the range. So we create this type of list. So now all the years, suppose now we simply create label list and WDF list. Okay, all the year for all the year. So further we simply create a we need to create a empty list. Okay, this empty list including all of the year. Suppose 2040, 4.5, 2040, 4.5 or 8.5. So basically we create that, we apply the two model. Okay, so RCP 4.5 and 8.5 for the 2040, then 2060, 2080. We apply. So in this case, we simply create a empty list. Suppose label list equal empty, and also put the WDF list. It also empty. So we add the later after that, and also all year list. So all year list. So we simply create the three empty list. Okay. So now we simply apply a loop function, and then we simply apply all of year for the two model 4.5 and 8.5. Again. So let's go try to apply. So I take a variable source for year range in zip, then call the wire list. This one, this is the list, and also call the wire range list. Range list. So now we put a loop and apply for RCP in list. RCP list. So now apply WDF equal, call the prepare this library, prepare LRS weather, this one. and then put the get file path. Define the file path. CP C art CP and RCP, and put the bracket and write here the RCP. RCP. It's a lowercase. RCP. This variable RCP. And also apply year range. So this is the year range. Let's paste year range. And then put the unit WG dot get. This is the unit about that. And further, we mention also year, year, and also apply true. Then we simply create a order list. Suppose this is the order, just I copy. And then paste here. So here, this is the order, simply paste in here, same. Okay. And now we're simply connecting all of those. So WDF dot list WDF list. So this variable WDF list dot append with WDF. It's simply connecting. Then also level. So level list it append with we write manually append app RCP by 10. Then we create the new line. Create the new line and put the year range. So year range is year range. And finally, okay, this is the put in here. And finally, simply all year list. So all year list, it will be append. All year list append with YR. So now let me run the code. Okay. It show the no files as directory users. I think some problem in your directory when I said, let me check it. One is for let me try to check for a correct or directly from here. Because get file function is CP is this usually means that file name is incorrect. So this is the all of data. I think this one. So now we try to apply it. So representative concentration pathway, RCP. We simply apply this model, okay, and project future prediction. So let me check it. So we are applying this model, okay, RCP 8.5 and also RCP 4.5. So RCP 4.5 represent the stabilization in radiative forcing. 4.5 is post to 2220 to 2100. Yeah, this one. 4.75 and then the RCP 8.5. We simply use it. But it don't find out that directly. Let me try again. Okay, done. So now it's working. So now if I just call, I want to check suppose level list. So level list. So this one I need to check it. Okay, just take copy. And then I check it. So if I know that you can send for RCP 4.5, we get 2021 to 40. RCP 8.5 at 2021 to 40. RCP 4.5 2041 to 2060. RCP 8.5. So we find out that all of those for the two climate scenario, 4.5 and 8.5. Okay. I want to check suppose WDF list. We find out all of this. You can see the minimum, maximum, reference date. All of this find out that. I want to check suppose all year list. This one. Just take the another cell. We find out 2030, 50, 70. Okay. 2030, because I simply choose 2030, 50, 60. So 2030, I need to create two climate scenario model, 4.5 and 8.5. 2050, 4.5 and 8.5. 2017, 4.5 and 8.5. So that's why I can see we find out this type of output. 2032 time 4.5 and 8.5 scenario. 2050, 4.5 and 8.5, and 2070, 4.5 and 8.5 scenario. Okay, so that's why we create this type of data. Okay, so now we find out this type of data look like that. So now we try to compute the concentration. Okay, carbon dioxide concentration scenario list in the order. Okay, so we try to identify carbon dioxide concentration scenario listed in order. So if you simply search here, suppose aqua crop CO2 carbon dioxide concentration. So you can see this is the, okay, it's not. So you download this PDF and read all of those more better. So this is aqua crop water productivity model. So you can get all of those more information. How to aqua crop input. Okay, what types of input, what is the application. So I'll just send you this book. You also try to read, then you get the more better idea. Aqua crop standard window program versions of aqua crop plugin. So aqua crop GIS. And now we also it's also developed the aqua crop os.py. So now, okay, so let me open this scenario. So in this case, I try to explain again, then you can get the better idea. So first of all, we simply import our SAM model, okay, and also import this type of library. And then we simply call our one data cp.dat. So this data, it's a ready-made product or ready-made data is available. So then we simply create the prepare the LARS weather data, okay, for all of year, including all of year. And then we simply create the list. So in this time, we simply define a list containing numbers that like corresponding the different representative connection pathway, basically RCP, representative connection pathway list 4.5 and 8.5, which is our standardized climate scenario. In climate science, RCP 4.5 and RCP 8.5 are common scenario, representing different level of future greenhouse gas emission. Okay, so this is the RCP 4.5 and RCP 8.5. It's our common scenario, but it's representing different level of future greenhouse gas emission. Okay, the value 4.45 and 85, basically 4.5 and 85. We simply in the list are likely is short for this scenario, and we simply define a list. We also define another list. You can see this is the list 203 30 2050 2070. It define a list of specific target years. Okay, so which year you want to target. we simply define this target year. So your target year, it can be different, there is no problem. So it's a target year, it's our target year. So 2030, 2015, 2070, there's these are likely are the center point of representative years of the different future projection period. So then if you check, we simply take the range list. So this range list, why we should take, so it defines a list of string which each string represent a multi-time span. Suppose 2021 and 2040, 2021 and 2040 corresponds with the target year 2030. Okay, 2041 and 2060, this corresponds the target year 2050. 2061 to 2080, this corresponds with target year 2070. Okay, we simply get this type of year range. So after that, we simply take some, you can see we take the empty list, label list. So it will store descriptive label for each scenario year combination. Then WDF list, it will store the actual process weather data, likely pandas data frame. Okay. Then all year list, basically it will store target each year associated with the each pre-processed data frame. Okay. So then we simply create the loop. So we simply create the loop, start and outer loop. So it iterates over pairs of items for year list and year range list at the same time. And this is done using the zip function. Again, we also use the zip function, you can see. And on the first iteration, year list, year, year, year. So year will be 2030 and year range, this range will be 2021 to 2040. Okay. So then second iteration, year will be 2050 and year range will be 2041 to 2060. Okay, then if I 2050. And finally, third iteration, year will be 2070 and year range will be 2061 to 2080. Okay. We simply create this nested structure, ensure that code inside will process very combination of time period and RCP scenario. For example, it will be process 2030, 2021 to 2040 RCP 4.5, then 2030, 2021, 2040 8.5, that move on the next year period. Okay. So after that, we simply create a WDP prepare list weather get file. So if you check WDP per LAR's weather file, so get file. So this is the key data processing step. It construct a file path, gets that path, and then process the data file at the location. So in this time, you can see simply put this location EC CP art. So CP art, the name look like they follow a standard pattern for data from the EC art global climate model. Okay, EC art global climate model process with LARS WG data. So you simply search, then get the better idea. Suppose I simply search here EC art EC art global climate model. So you can see this is the EC art. So you also get all of the information from this EC art. We simply use this model. Okay, EC art. It's a European Community Art System model. Okay, so you also use it in this time. So you can get the different types. You can see the EC art 2, EC art 3, EC art 4. So it also upgrading. Okay, so EC art global climate model proceed with the LARS SWG. If simply search here, suppose what is the LARS WG. Okay. Data or download or generator, you can say download. You can see this is the Win download set on Jeven, you can see here. So WRG WG, weather generate for climate change. Okay, so I'll already check this type of thing. You can see this. We can find out a lot of data regarding this type of climate data, climate scenario with WRS, WG. Okay, so this is the one kind of data, climate scenario data. We also use it. Okay, this type of data, WG. So then this is the path. We simply call our path, and then we simply define the prepare large weather. This is the main function. Okay, prepare large weather. So this is the main function. This is the main function. It likely does the heavy lifting of reading the data file, parsing its contents, and performing the necessary calculation or conversion specific to LRS WG output, and retaining the result as a structured format, almost pandas data format. We find out the data. Okay, this function help me this type of data. And finally, we simply call all of those one by one. We also use, you can see the YR. YR basically the current target year from outer loop. This function might use this time stemming or categorization. Suppose for different year have the different category, 2030, 2040, 60, 80. And true, it's a boolean operator. Basically, this is the blue flag. Its purpose depends entirely on how prepare large weather is defined. It might enable a certain feature like daily, monthly, or aggregation, and data column creation or data cleaning. Yeah, okay, so need to see the function contour combination to be sure. Okay, just we put the true operator. So further is simply just append. Basically, it takes the weather data that was just created and add it to the end of this variable. Okay, this variable using the append function is simply add, connecting all of those. Okay, then it create this type of, you can see RCP for the different scenario, RCP 4.5 and RCP 8.5 for different year. Okay, 2021 to 40. So 2021 and 40, it's indicating which year? It's indicating year of 2030. Okay, then 2041 to 2060, it's indicating year 2050. Then 2061 to 2080, it's indicating about the year 2070. And we apply the model for 4.5 and 8.5. Okay, two scenario. So that's why we upgrade for the two time. Okay, so you can show it create for the all are the two times, and we find out all of information. So now we discuss about the carbon dioxide concentration for the scenario listed in order. So now this is common. This is the comment. If you check, suppose it inform the reader that the next we find out the carbon dioxide concentration. Okay, so suppose I simply write a comment, then you can get the idea. That was carbon dioxide concentration. Concentration, carbon dioxide concentration. So now I simply create the list. So that in here, suppose CO2 list, and I say put the list, suppose 435, then 449, then 487, then 541, then 524, then 677. So in this case, you can we simply use some number. So define a list of numbers representing carbon dioxide concentration in parts per million. Okay, parts pp unit, ppm unit, and these are likely the specific average carbon dioxide concentration assumed for each of the 6 scenario. Okay, in that order, for example, suppose 435 is for RCP 4.5, and 2021 to 2040. Then 449 is for RCP 8.5 and 2021 to 2040 and so on. Simply apply others. Total 6 we have. Okay. Then further we simply check, suppose just run it. And this is the ppm. Now call WDF list, this one, and we simply apply the index. Suppose WDF list, we take the first and also get the head. So now you find out, you can see this type of information. So now this is the large generated output file. Okay, this is the LARS generate output files. In this example, it's comprised of 100 years of daily weather data. Okay, daily weather data denoted by the same year. Okay, daily weather data. And then to select any of those years, we simply use the function and select for a specific. Suppose I simply choose another one. Suppose I just call the select simply call this library, this one. And we simply choose a specific year. So for that, just we call the WDF list, WDF list, and take the first index. Then I put our same year equal to suppose 3. Okay, then I put the head. So now you find out, you can see all same year is for 3. Okay, so this is the large generate output file. We find out that, okay, it comprises 100 years of daily weather data, denoted by this column. If you check the same year, this one. Okay, so this one, so it's daily weather data and it denoted by same year column. We can simply select a specific year and then choose. Okay, suppose I put the 4 and run it. So now I can get for this data. Suppose I put the 9 and run the code. So you can get the data. Okay, 100 years. 100 years of daily weather data. Okay, so you can simply put any year or daily. Okay, so now our all of data is ready. So now we can easily apply our model and check the result. Okay, do you have any question? You can ask me for any data preparation process, for because it's some EC data or also RCP at the same time we combine as well as LARS data format we also combine. Okay, so any question you can ask me, then I try to explain again.
So far I do understand.
Yeah.
What you read.
Okay. Thank you. So now we simply apply crop soil irrigation configuration. We simply apply the model. So let's go try to write our model, then I explain. So I just take a variable, suppose crop, and then call the crop library and write our model. So we simply choose the Maize. It's our crop type, MAIZE, Maize. Then planting date. So planting date. So we simply put the planting date equal 0501. Okay. So first of all, we simply choose our crop, initialize crop object of Maize using the calendar day mode. So calendar type, which is ensure the growing season. Okay. Calendar type is ensuring this is the very important planting date. So calendar step the crop planting. Okay, so for this it display the planting start from May 1st. Okay, start the crop planting date to May 1st. So then calendar type, so then we say for the calendar type, calendar calendar type. Calendar type, suppose one. Okay, so it specifies that crop growth parameter are driven by calendar days rather than growing degree days. Okay, so it's indicating about that crop growth parameter are driven by calendar days rather than growing degree days. After that, we simply define another, it's called the emergence. So so let's suppose 6. So emergence, this set the numbers, this number day after planting until crop emergence to 6. Okay. Then also have suppose different types of arguments. So max routing, we can also apply maturity. Okay. Then also sen sense, we also use set the total number of days after planting until leaf census begins. Okay, so we'll say apply emergence, or we apply suppose this one is the then yes CSENCE. Okay, so suppose 107. So this number set the number of days after planting until leaf census begins to 107. Then we'll say apply suppose another, it's called the max routing. So max routing. Max routing, it defines the days after planting when maximum routing depth is reached. So suppose 108 days. Okay, define the days. It define the days after planting when maximum routing depth is reached. Then maturity. So we simply define the maturity. Suppose maturity. Suppose 132. So maturity 132. This sets the crop maturity timeline to 132 days after planting. Okay. Then we also apply suppose SI harvest index. Basically, SI harvest index start. So SI means harvest index. So it defines the days after planting when harvest index accumulation start. Okay. So it defines the days after planting when harvest index accumulation starts. 66 days. Okay. Then flowering. So a lot of primary kernels wondering. So it's flowering. So following equal to suppose 13. So set the duration or timing parameters related to the following. Okay. Then we also apply suppose yield formation. Yield formation basically YLD, yield formation, form, FORM, yield form, mainly yield formation. Okay. Yield formation was 61 days, suppose. So set the start of the yield formation period to 61 days after planting. As well as you can also mention another, suppose it's called the canopy decline coefficient. Okay, canopy decline coefficient, CDC, canopy decline coefficient. We said suppose 0.117. So this is a set canopy decline coefficient. As well as also canopy growth coefficient, it's called GCP. Okay, canopy grow, sorry, GCG, CGC. It's a canopy growth coefficient. So was 0.163. This is the canopy growth coefficient. Okay. So this type of factor we can also consider in our model. So I again explain. So first of all, we simply define our crop type. So initialize a crop object for maize. So we simply set the maize. Then planting date. Planting date, it indicating about the set the crop planting date. Okay, set the crop planting date. Suppose 1st May. Okay, 1st May. Then calendar type. Calendar type specifies that crop growth parameters are driven by calendar days. Then emergence. Emergence, the number, it's indicating the number of days after planting until crop emergence to 6 days. Okay. Then senescence. This one, the set the number of days after planting the until leaf senescence beings 170 days. Max rooting. Okay, max rooting indicating about that after planting, define the days after planting when maximum rooting depth is reached. Then maturity. Maturity, set the crop maturity timeline. Okay, to 132 days after planting. Then harvest index start. So SI start, define the days after planting when harvest index accumulation start. Suppose 66 days. Following set the duration or timing parameters related to following. Then yield information period. Okay, so suppose this one, yield form. Okay, yield form indicating about that set the start of the yield formation period to 61 days after planting. Then CDC basically canopy decline coefficient. GCP basically canopy growth coefficient. We simply define all of this. Okay, so we simply combine this type of thing, we simply apply. As well as we also apply another, suppose create the soil type. Okay, soil type we can also mention. Okay, so let me run. Is there any problem? Let me run it. Oh, there is no problem. It's okay. So now I simply choose suppose soil type. So take a variable suppose soil. Well, I simply call the soil library and define suppose soil is the clay loam. Clay loam. Clay loam. So then we simply define the initial water content. Okay. So initial water content, WC. So I simply call the initial water content function. So initial water content, this library simply call. Okay, default is field capacity. Okay, default is the field capacity. Okay, so we put the default. And then irrigation management. So irrigation management equal. We simply call the irrigation management library. And so irrigation management, define the irrigation management strategy. So we simply put the suppose one basically indicating about that threshold based irrigation. Okay, we already know about the different types of irrigation strategy. Okay, one is referred that threshold based irrigation. Okay. Then we simply apply SMT. SMT basically soil moisture target. SMT. So SMT, soil moisture target, we set 70% available. 70%, suppose 70% water content, 70% by 4 to cover 4 distinct stages. Okay, so for that 70 multiply 4. Okay, so SMT, it's a set the soil moisture target threshold to 70% available water across growth stage. Multiply 70 by 4 to cover 4 distinct stages. Okay, 4 distinct stages. We simply multiply this type of things. So now let's check what happens if I run. Okay, there is no problem. So now after that, after all of parameter is ready, crop, then soil, initial water content, then irrigation management. So then we simply set our model. Okay, suppose I simply create the model. So just take a variable model equal. I simply call aqua crop model, and I define the start date of the baseline simulation, the in date baseline simulation simply define, then baseline weather input data set, and also all of data, soil, crop, initial water content, simply define all of those, and irrigation management, all of those simply define and create the model. So we simply define the start date baseline simulation 1982 0501. It's a start date baseline simulation. Then in date of baseline simulation 2018 10 about 30 in date. Then we define the baseline weather input data set. So baseline weather input data set, it's a LARS base. So LRS we already defined. This one, LRS. I think, let me check. Label. WDF list. LARS base. This is this one. Then soil. We already defined the soil. Then we already defined the crop. So crop. Then we already defined the initial water content. So init WC. Then we define irrigation management. Okay, so irrigation management we already defined. So irrigation management. So and right, suppose irrigation management equal this one. Define. So now we simply input all of parameter for our model. Okay, so we simply have start date, in date, then large space weather data. Okay, large space weather data frame with shape. You can see how much data, 13,787 and 5 column. Then soil, then crop, then initial water content, irrigation management. We also define. So run the code. So now let's say it will create the model. So this model further is simply run. So we simply apply model. dot run. So run this model, model dot run model, sorry, run model. This function model dot run model. So then we simply apply till termination equal true. So till termination equal to true, it tells the model to run through the entire timeline. Okay, so this till termination true, it basically it tells that model to run through the entire timeline until the end date or crop life cycle completion. Okay, so now I run the code. I hope there is no problem. It will work. Now it's successfully run. We find out that. Okay, so now model is created. So we simply get that represent the confirmation output returned by run command true. Okay, it's mean the indicating the success. Okay. So now we simply apply the model. Okay. Suppose we simply simulation. So I simply apply. So create a variable. Suppose baseline yield. Baseline yields equal. I create the list. Suppose I create the list model. I simply call the model dot get simulation. So get simulation result. Get simulation result, and I need suppose yield data. So just I put here yield, yield ton per hectare. So ton per hectare. Okay, and I need only values. So just I put here the dot values. So in this code, we simply apply the we simply retrieves the result data frame, generate the simulation run, and extract the yield ton per hectare data as a column. Okay, and convert those values as a list. Okay, and store in this variable. So now let me run the code. Oh my god, show the problem. What's the problem? Yield. Okay, check the indexing error oil arise if we have the list like key. So I think I need to put the space in here. Okay, ton is so now run the code. Okay. I think what's the problem? This is the start bracket and this is the end bracket. Well, find about another bracket. So list model dot get simulation result. Now let me check the column name. So this is the harvest date. This is the harvest date. Dry yield ton per hectare, yield potential ton per hectare, seasonal irrigation, fresh yield, dry yield. Okay, I think we need to choose this type of name. Fresh yield or dry yield. Yield potential. So this one. So I just use it. Copy. And this thing I simply apply in here. Okay, so nice work. So now from here, any column, you can see it show the different types of yield. Fresh yield, we find dry yield, okay, fresh yield, yield potential, ton per hectare. So anyone just simply copy the column name and then we can easily make the so now further if you just simply call it, now it's just great only for this type of yield. We find out that. Hmm. So then suppose I need seasonal irrigation millimeter, how I can do it, how I can make the list. Same way, just I use the same line of, then create the another port. Test here, suppose I put the variable name is baseline irrigation. Suppose baseline irrigations. So get simulation result, then call the seasonal irrigation column. So if you check, you can see seasonal irrigation millimeter. Just I call it and change. So now run the code. So now we can get the another list only for baseline irrigation. Okay. So now we simply compute the baseline level. Baseline levels equal baseline. It's it's multiply with lane of baseline lane of baseline irrigation. Just type okay. So I find out that baseline and it computed the baseline of irrigation. Okay, so now we created another model function that run aqua crop for 100 years of the climate scenario and future prediction. Okay, so for that, how I can do it? Okay, and also use the carbon dioxide concentration or atmospheric carbon dioxide concentration. Just Okay, so basically, okay, what if I need to use the growing degree days instead of the calendar days? So calendar type 1. So in this time, if you check here, I use the calendar type 1. Calendar 1. So calendar type 1, calendar days mode, fixed duration, okay, regardless of temperature. But calendar number 2. So when I put suppose calendar type is 2. So it means that growing degree days mode, degree Celsius day. So growing degree days mode, higher crop phenological development dynamically adjust according to the daily ambient temperature, minimum temperature and maximum temperature. Okay, so when I put that calendar number 2, so update crop phenology parameter to thermal time, degree Celsius. When using calendar type 2, all time different parameter, which are previously entered in days, must be specified the cumulative GDT, okay, from the planting, suppose emergence GDT, then also maximum root, then also census, maturity. So all of those, okay. Then harvest index start, GDT start harvest index accumulation, following length and timing GDT, okay. Then canopy growth decline coefficient per growing degree days rather than per calendar day, okay. So canopy growth and canopy growth and also decline the coefficient per growing degree days rather than per calendar. So if you want Aquacorp's default thermal parameters for mice, you can simplify, specify calendar type 2 without hard coding calendar day values. Okay, it's also possible. You can also use the calendar number 2 without hard coding. Okay, and also customize the parameters in GDD mode. GDD mode, we need to customize all of those in the GDD mode. Okay, when you apply the calendar number 2, when I apply, then I need to customize all of those in the GDD mode. Okay, customize all parameters in GDD mode. So it's very important because temperature sensitivity. Okay, in warmer climate, sensor accumulate GDD builds faster, naturally shorting the growing season. In cooler climates, growth the slow down, as well as also transferability. So unlike mixed calendar dates, GDD calibrate parameters allow the same cultivator to adapt the accurately and regionally climate difference and climate change scenario. Okay, we find out that. So when you use the calendar type 2, then you must need to customize all of other parameter. Okay, degree Celsius. Okay, degree Celsius days, degree Celsius GDD. We need to convert all of those. Okay. Otherwise, you can put the one calendar type 1, but then just apply this type of things, no problem. So this is the degree and days, two types of calendar, 1 and 2. So let's go try to create this model. So now it's simply create a function def, suppose run model. We create this function and we put their total 3 arguments. So all WTF data, then CO2 concentration, another is the ER. Yeah. So 3 elements we simply choose. So GN yields, we put the empty, and also gene tears, so let's put the empty. So now we simply apply the range. Suppose 100 years. So for I in range, for I in range, 100. So now call the WDF equal, we simply call the sled WRs WD, and then we simply apply suppose W all, and also it increment one by one. So we simply put that comma I plus one. So one by one increase all of those. So after that, we also define the carbon dioxide concentration. So just take a variable, suppose CO2, carbon dioxide, and then call the CO2 library, and we define constant concentration equal true. Okay. And then CO2, carbon dioxide dot current concentration dot current concentration equal to carbon dioxide concentration. We simply define in here again. So now we define all of those. We simply create our loop. Now we apply the model. So model 12. So just put the aqua crop model and define the ER. Okay. So aqua crop model app, we define the ER. Okay, so it's come from we simply input suppose ER. Then we put the date 0501. Then put the comma sign app, define the year we later, so year. Then put the 10 30. Then we define our data WDF, then soil, then crop, okay, as well as your initial water content. So initial water content we also define. Then define the irrigation management. So irrigation management equal to this variable, okay, and also define the carbon dioxide concentration. So just define the carbon dioxide concentration CO2 concentration. Okay, CO2 concentration equal to CO2. Okay. So we define the model aqua crop. Okay, aqua model. I hope there is no problem. Okay. So now we simply run our model. So define model dot run model. So run model. So model dot run model till termination true. And then we simply call our this yields, generate yields append with its model get simulation result, and call the yield potential ton per hectare, as well also get the this one okay, this one irrigation, okay, and return the yield and irrigation. So now let's check what happened. Okay, okay, there is no problem. So now I want to pray and get the result. Suppose this one, I want to check. Oh my God, seal model is not defined. Okay, so we create the function. Okay, so this is a function variable name. So this function variable name further we simply connect, then it will work. Now for each combination of climate scenario and projection period, run aquacrop and save the result. Okay, so now let's try to do it. Suppose all yields, we make the empty list, then all irrigation, then all levels. Okay, we create the three empty list. So now I apply for loop. So for I in range, we put suppose 6 years for three into two, because we show the result for RCP 4.5 and 8.5. So 3 into 2 multiply to 6. Okay, 6 years. And we put the year 12, all year list. And then WDF equal WDF list. Okay. After that, carbon dioxide CO2 equal to CO2 list, and label equal label list. Okay, so we simply define. So now all yields, and also y YLD yield. We take the new variable, so YLD list, and also take another variable irrigation list. And we run our model. So run gene model. So just I simply call the function. So here's I use in here. Okay, this function I simply call run gene model, and then apply the data WDF, carbon dioxide, and year. Okay, so now further we simply append with our YLD list, then TIRL list, and also label. So this label we just also apply, I think we need to the extend function, not append. So put the extend. Also extend label, it's multiply with lane of yield list. So basically 100 years. So lane list. This is the better yield list. Basically 100 is simply multiplying here. So now let's check. So now it just apply for the two different temperature scenario, 4.5 and 8.5. Total 6 years. 6 years, basically 3 years for two model. 3 years for two model. So that's why it created the total 6 result. We find out that.
বাঙালিরা সব থেকে বেশি
Okay, just we are make a break for 10 minutes. In the meantime, it will be working. We are make a break for 10 minutes. Okay, so welcome back. So let's please start. So it's
Okay.
successfully executed, yeah, all of those. So now we try to check our data, what types of result we find out that after running this model, basically yield and irrigation. Okay, this type of thing we try to check. So just take all the all yields, then it will run. So it give me the all of result. Okay, we can easily get, but we can create the data frame, basically pandas data frame format. Okay, so then we can easily make the chart or others. Okay? All levels extend. So we can say all of data is ready. So now we try to, we can see it also for the RCP 8.5, RCP 8.5. Okay, so now we try to create the data frame. Okay, then we can simply create the chart or other represent using the data frame. So now how I can convert this type of data as a data frame, mainly pandas data frame. Okay, so combine projection result with baseline, and we convert all of data as a data frame. Okay, suppose yield and also irrigation millimeter. Okay, so all of these two column, and also level basically baseline. So I take a variable, suppose all yields equal, I simply call the baseline yields, plus all days, all yields, plus all yields. And also get the baseline irrigation plus all irrigation. Okay, baseline levels plus all levels. Okay, yesterday these type of things. So now, okay, now we simply import our pandas library to create the pandas data format. So import pandas as pd up, oh sorry, pandas. So further we simply create the pandas data frame. So df equal pd dot data frame, and further we simply call all of those, suppose all yields, this this all irrigation, then all levels is a baseline. Put it here, and we simply put the dot p, and then df dot columns, we set the columns equal, I said suppose yield, then put the irrigation, total irrigation, then set the another column is the baseline level. Okay, level. Not the problem. Make the list. Oh, sorry, CO columns. Hit the rotation and that's okay. And also we call the df dot head. Okay, so yeah, okay, so it's a list. We have to use the square bracket for the list square bracket. So now let's check. Yes, done. So we find out this type of things. Yeah. So all of those yield, and also get that irrigation, okay, and also baseline. All of this you can get this as a column. Or you can simply check suppose BDA, DM, and it give you can see all of those. I find out that total 222 rows and 3 columns about our data. So now further we simply create our plot to represent different types of figure. Total irrigation, also total yield, okay, ton per hectare. Basically, this is our data set. Okay, so this data set further we simply use. I can see. So it show of data. Further, we simply create the chart and display this type of data. Suppose import matplot dot pyplot SPLT, import C1. So we simply type in the fig and axis. So we simply call the PLT dot subplot, PLT dot subplot, and define 2 row 1 column. Okay, 2 column 1 row, 2 column 1 row, and put the fig size equal suppose 12 by 14. So now it create this type of figure and further it, oh my god, see subplot 1 2 are given. Nice. Subplots, it will be subplots. Okay, so now we define SNS dot box plot. So data equal to TF, X equal to level, Y equal to field, and X equal to 0. Okay, just we run the code. We generate this type of yield. We find out that. So now I want to create suppose another for irrigation. So same way, SNC box plot, TF, X level, Y irrigation. So now it also generate about that another. So you can get the irrigation. Okay, so we find out that irrigation as well as we can also add the level and font size or others information. Suppose okay, I keep the default. We create the yield potential ton per hectare. Again, okay, I think it's a big size, so that's why it's okay. So we find out you can see this type of things. This is the yield and this is the irrigation, baseline irrigation. We find out that. So this is the way how to combine the two predicting RCP 4.5 and RCP 8.5 for different climate scenario and predict the yield and predict the irrigation demand of irrigation or water demand we identify. Okay, for future prediction we'll use. So this is the way. So I will send you this code. You also try to practice again for this type of way. And from the next class, we discuss about the machine learning concept. Okay, so how to use the different types of parameter and help of machine learning, and then how to predict for yield. Okay, so now I hope you can also get the idea about the aqua how it will be work for using the different types of parameter. So you also try. If there is any problem, you can also inform me. I also guide you, inshallah, no problem. Yes, any question, please?
Okay, I will do the practice and then once I
Yeah.
the
Yeah, so
problems,
you
I will
try.
let you know.
But if there's any problem, also inform me. Then we'll also try to solve the issue. No problem. Okay. So I will send you all of materials as soon as possible. You try to practice. Okay. And next class will be held on the next Tuesday, inshallah. At the same time, we will meet and discuss. Okay.
Okay.
Okay. Thank you for joining. Have a good day. Bye.